On January 28, 1986, Space Shuttle Challenger rose from Launch Pad 39B in Florida. For a little over a minute, the flight looked normal. Then the launch vehicle disappeared inside a vast white and orange cloud as millions watched live. The failure seemed to happen at 73 seconds, but the accident had begun before Challenger cleared the tower, and the conditions that made it possible had been building for years. At the center of the investigation were two rubber seals inside a joint on the right solid rocket booster. The rubber itself was only about 0.280 inches thick, but each seal ran around a booster more than 12 feet in diameter. Their job was simple: keep the booster's combustion gas inside. So how could an O-ring help destroy a space shuttle? And why did Challenger launch after engineers warned that the cold could make those seals unsafe? The night before launch, a hard freeze settled over Kennedy Space Center. Ice formed around Pad 39B. Inspection teams went out 3 times, and the countdown was delayed to give the ice time to melt. At liftoff, the air temperature was 36 degrees Fahrenheit, about 2 degrees Celsius, 15 degrees colder than any previous shuttle launch. The coldest point on the failed booster joint was later estimated at about 28 degrees Fahrenheit, with an uncertainty of 5 degrees. That mattered because the solid rocket boosters were not single tubes. Each one was made from large steel segments, joined at Kennedy Space Center. At every field joint, the narrow end of one segment, the tang, slid into the U-shaped clevis of the next. 2 rubber O-rings sat inside grooves in the clevis. The first was the primary seal. The second was the backup. When the booster ignited, internal pressure rose almost instantly. The steel walls flexed, and the joint opened slightly. A warm O-ring could spring outward and follow that movement. A cold one recovered much more slowly. In commission tests, a compressed O-ring at 75 degrees responded about 5 times faster than one at 30. If the seal did not move quickly enough, hot combustion gas could blow past it. The backup O-ring sounded reassuring, but joint movement could also pull that second seal away from an effective sealing position. Under these conditions, redundancy existed on paper more than it did in practice. This was not an entirely new concern. Previous shuttle flights had shown O-ring erosion and blow-by, soot and hot gas passing the primary seal. The problem had been tracked, analyzed, and repeatedly accepted without a complete redesign. On the afternoon of January 27th, Morton Thiokol engineers learned how cold the launch pad was expected to become. Robert Ebeling gathered colleagues including Roger Boisjoli and Arnold Thompson. Their flight history was limited, but its direction was troubling. The coldest previous flight had also produced the worst blow-by then seen. During a long teleconference that evening, Thiokol's engineering position was clear. Do not launch until the O-rings reached at least 53 degrees Fahrenheit, the lower edge of previous flight experience. NASA participants questioned whether the available data supported such a strict temperature limit. The dataset was incomplete and messy. It could not predict whether an accident would happen, but it also could not show that the system would work safely in the conditions forecast for the morning. Thiokol managers went off the conference line to caucus. The engineering objections remained. Management reversed the company's recommendation and sent NASA a written rationale to proceed. The deeper failure was not one person ordering a launch against everyone else. The risk had not been resolved, and the evidence had not become stronger. Yet by the end of the discussion, the decision was to accept it. The initial no-launch recommendation and the engineers' continuing opposition did not reach senior shuttle managers with a complete account of the dispute. The issue was treated as resolved at a lower level. At 11:38 a.m., the countdown reached its final seconds. At T-minus 6.6 seconds, Challenger's 3 liquid-fueled main engines started. Their thrust bent the entire stack slightly forward while it was still bolted to the pad. The vehicle then sprang back upright. At 0, the solid rocket boosters ignited. Their internal pressure raced toward operating level in roughly 0.6 of a second. The hold-down bolts released. Challenger began to rise. This was the moment the field joints faced their harshest opening motion. The right booster's aft joint was cold, its steel case was flexing, and its O-rings had milliseconds to seal. At 0.678 seconds, a camera recorded a strong puff of gray smoke from the right booster's aft field joint on the side facing the external tank. From 0.836 to 2.500 seconds, 8 additional puffs appeared, each darker than the first and pulsing with the vehicle's structural vibration. Their color suggested that grease, insulation, and rubber inside the joint were burning and eroding. No similar smoke had been found in films of earlier launches. Then the visible smoke stopped. Investigators considered 2 possibilities. A small leak may have continued where cameras could not see it, or molten aluminum oxide and combustion debris may have formed a fragile plug across the damaged seal. For almost a minute, the flight looked normal. The main engines throttled down as Challenger passed maximum dynamic pressure, then began to throttle back up. But a temporary plug is not a repaired joint. Steering movements, vibration, and changing winds could break it open again. At 58.788 seconds, enhanced film revealed a tiny flame at the same right booster joint. Less than half a second later, it had grown into a continuous plume. The high-speed airflow bent the flame backward and around the booster. It struck both the external tank and the lower strut connecting the booster to the tank. At 64.660 seconds, the plume changed shape and color. Telemetry showed that hydrogen was leaking from the external tank. Challenger's computers continued correcting pitch and yaw. From the cockpit and mission control, the systems still appeared to be doing their jobs. At about 72.2 seconds, the weakened lower booster attachment failed. The right booster began rotating around its upper attachment. At 73.124 seconds, failure of the liquid hydrogen tank's aft dome began. Massive quantities of hydrogen escaped, driving the tank forward into the structure between the hydrogen and oxygen tanks. At almost the same instant, the rotating booster struck that structure and the lower liquid oxygen tank. At 73.137 seconds, the external tank structure failed further. The launch stack then rapidly lost overall structural integrity. Challenger was traveling near Mach 1.92 at roughly 46,000 feet. Hydrogen and oxygen burned in the enormous fireball seen on television. The orbiter, suddenly exposed to aerodynamic and inertial forces far beyond its design limits, broke into major sections. It is often called an explosion. Visually, that is understandable. Technically, the Commission described an explosive burn of released propellants followed by structural breakup. Recovered orbiter fractures showed overload, not evidence that the crew cabin or orbiter had detonated like a bomb. The Rogers Commission identified the direct cause. The pressure seal failed in the aft field joint of the right solid rocket motor. The design was unacceptably sensitive to temperature, dimensions, materials, reuse, processing, and dynamic loading. But the O-ring failed is only the first layer. The Commission also found a flawed launch decision, incomplete and sometimes misleading information, a conflict between engineering evidence and management judgment, and a structure that allowed critical safety problems to bypass key shuttle managers. Years of partial seal damage had changed the meaning of evidence. Because previous missions survived erosion and blow-by, abnormal performance became something the program learned to tolerate. Successful flights did not prove the joint was safe. They gradually made the warning look familiar. The shuttle fleet remained grounded for nearly 3 years. The redesigned solid rocket motor joint added a capture feature to limit joint opening, a third O-ring, improved thermal barriers and heaters, along with extensive full-scale testing. NASA also created stronger independent safety oversight, reviewed critical hardware, changed management and communication practices, and added a limited crew escape system for controlled flight. Discovery returned the shuttle to flight on STS-26 in September 1988. Challenger's lesson is larger than one seal. Complex systems rarely fail because of a single dramatic mistake. They fail when technical weakness, uncertain evidence, schedule pressure, and broken communication line up. And each small exception is accepted because the last one did not end in disaster.